I'm not sure when they'll get the bells ringing, but without that, we'll just start when it's 2 o'clock. So if you did not get a copy of our information sheet last time, you can raise your hand now and I'll drop one off for you, or if not, you can also come get it. And then if you didn't turn it in last time, please just make sure to turn that in on your way out of class today. Okay, let's go ahead and shut our exit door over here so have less noise from the hall. Okay, so a reminder to bring your iClickers on Friday. That's when the iClicker quizzes can begin. And then today we're going to discuss bonding briefly and spend most of our time talking about Lewis structures and resonance structures, two very closely related topics. So bonding is a topic that you will have studied quite extensively in general chemistry. So we won't spend a lot of time on bonding. But there's just a couple of things I want to mention about bonding first before we move on. And one of those is that bonding is an energetically favorable process. As you take two atoms and link them together by a bond, the electrons move to a lower energy level. Okay? So it's a favorable process, and it has to be a favorable process, otherwise molecules would not exist. If the other way was favorable, if by breaking bonds, energy was released, then all the molecules in the world would spontaneously fly apart. Life as we know it would cease to exist, and we would just have individual atoms floating around. Okay? So obviously that cannot be true. So we know it has to be the other way around, that bonding is energetically favorable, and it lowers the energy of electrons that are involved in those bonds when compared to the unbonded atoms. And that's important because those of you who go on to study biochemistry, or you may have already studied some biochemistry, if you've learned about metabolism, if you've learned about the concept of ATP hydrolysis and how energy is generated in that process, in many biology or biochemistry courses, they will tell you that there's energy stored in bonds, and when the bonds in ATP are broken, that energy is released. That is 100% false. Okay, that is absolutely untrue. The people who teach it that way do have their reasons for making that oversimplification, but it is completely false. If that were the case, then as I said, no molecules would exist. Molecules would just spontaneously break apart, and there's no way we could have life. So what's really happening in ATP hydrolysis is weaker bonds are breaking and being replaced by stronger bonds in the new products that are formed. That's how energy is released. Okay? So please remember, bonding is favorable. Energy is not stored in bonds. That is not true. When you form a bond, the energy of the electrons involved in that bond are lowered. Okay? And then there's two types of bonding, ionic and covalent, which you know the definitions of. In organic chemistry, the vast majority of the time we're focusing on covalent bonding, where electrons are being shared between the two atoms involved in the bond. It's important to remember that that sharing does not have to be equal. We'll talk about this more towards the end of the chapter, but when there's a difference in electronegativity between two atoms, the more electronegative atom pulls on the electrons in the bond more strongly than the less electronegative atom does, creating a dipole. We will see a little bit of ionic bonding. There will be some molecules, typically negatively charged organic compounds, that then form ionic bonds with positively charged cations. Okay? Any questions about bonding? So it's important to know how many bonds are typically formed by each atom. And if we have atoms that are in the fourth column to the seventh column of the periodic table, we simply take their group number, or which column they're in. We subtract that from 8 due to the octet rule, and we get how many bonds they will form. So that's where the numbers in this table come from. Of course, hydrogen we know being in the first row, can only form one bond because it can only have two electrons. Okay. So what about boron? How many bonds can boron form? Okay, I see a few people putting three fingers up. Why can boron only form three? Who would like to raise their hand and tell us? Roger. Okay, and why is that? It is an exception. Exactly. It has three valence electrons, and so it can use each of those valence electrons to form three bonds, and that's it. Now, later on in the class, we will see boron with four bonds, but that's going to be a negatively charged boron. Okay, so a neutral boron can only form three bonds. It will have an empty orbital. It will only have 6 electrons as opposed to 8. Its octet is not satisfied. So as we will learn in chapter 2, that makes those neutral boron compounds quite reactive. Okay, so this 8 minus the group number rule only works for column 4 to column 7, carbon, nitrogen, oxygen, and our halogens. Okay? All right. So any questions about bonding and the number of bonds that atoms typically will form? Okay. Let's talk now about Lewis structures. Okay, Lewis structures. This is a topic that you have learned about previously. It's a very important topic because it lays the groundwork for understanding resonance structures, which we'll get into in the second half of the class today. Who can raise their hand and give us a nice textbook definition of Lewis structures? Okay. Anyone? Yes, please. Okay, a 2D visualization. That's a very good definition. They're flat, they're on paper. What do we use to represent electrons in Lewis structures? We use dots, exactly. So in our textbook definition of Lewis structures, we're going to refer to that. We're going to say that Lewis structures are electron dot representations of molecules. Okay. So they are two-dimensional. We'll get into three-dimensional structures in chapter 4. Of course, we know organic compounds have three-dimensional shapes. Whoops, I did not spell representation right there. There we go. So it's very important to understand Lewis structures, as I mentioned. And so there are a few key points to remember when we are drawing Lewis structures. The first one is that only the valence electrons are included. Okay, so we ignore the inner shells. So if we're looking at row 2 elements, we ignore those 2 electrons in level 1 in the 1s, and we only include the valence electrons. Okay, and then second thing we need to remember, each second row element, except for boron, which we already talked about, receives the octet if possible. If there are enough electrons available to fill all the octets, we will do that for all of our atoms except for boron. And each hydrogen atom will only have 2 electrons. Of course, we know why that is the case. Okay, so to draw Lewis structures, we need to remember these 3 points. We're going to go through an example of how to draw Lewis structures, and we're going to use a molecule called nitromethane as our example. Okay, nitromethane has the molecular formula CH3NO2. Okay? And we're going to go through a step-by-step process of how to draw resonance structures. Okay? So once you get skilled at this, you can combine some of these steps, but we're going to go through them step by step at this point in the class. Okay? Or how to draw Lewis structures. Sorry. I think I said resonance structures. Okay. So our first step that we're going to take in drawing a Lewis structure is we're going to arrange the atoms according to the number of bonds they form. Okay, according to the information we have in this table right here, which we don't need to memorize that table, of course, we can derive that. So we know that our hydrogens and our halogens are going to have to go on the periphery of our molecule as opposed to being embedded within chains and rings. Why is that? They only form one bond, okay? So they have to be around the periphery. Many times there's more than one way we can arrange the atoms. So oftentimes the information from step one is given to you as part of the problem. So in this case, we'll give it to you. We'll tell you that the 3 hydrogens are all bonded to the carbon. The carbon is bonded to the nitrogen. And then the nitrogen is bonded to each of the 2 oxygens. So lots of times step one is given to you. If not, remember that you have to have hydrogens and halogens around the periphery of the molecule, and it's going to be the carbons, oxygens, and nitrogens that make up the chains and the rings. Okay? All right, so once we have done that, then we need to count the valence electrons and then we need to make an adjustment if the molecule has a charge. Okay? So let's count our valence electrons for nitromethane. How many valence electrons come from our carbon? 4. How many valence electrons from hydrogen? 1. And how many hydrogens do we have? Okay. How many valence electrons from nitrogen? 5. How many valence electrons from oxygen? 6. And how many oxygens? Okay. So when we add up these numbers, we find that there are 24 valence electrons in nitromethane. Nitromethane is a neutral molecule, so we do not have to add or subtract any electrons for a charge. Okay? Any questions about step 2? All right. So let's move on to our third step, which we will split up into 2 parts. Once you get proficient at Lewis structures, you might be to that point already. You can combine these 2 steps, but we'll do them one step at a time for this particular example, splitting part 3 into A and B. So we're going to add remaining electrons to fill the octets of any atoms that don't have the octet as lone pairs. Okay, we'll abbreviate lone pairs as LPs frequently in this class. Okay? The table here is calling them non-bonded electron pairs. They're the same thing. Non-bonded electron pairs or lone pairs are very important in organic chemistry because they're usually higher in energy than bonded electron pairs. And so when we're looking at reactions, it's many times those lone pairs in the molecule that are participating in reactions. Okay? But for now, we're just trying to fill them in to draw our Lewis structures. So how many electrons have we accounted for by drawing in the sigma bonds connecting these atoms? We've accounted for 12. We've drawn 6 sigma bonds. That's 12 electrons. How many electrons do we have left to assign? 12, which means we would need 6 lone pairs. So let's go left to right. Carbon, do we put any lone pairs on the carbon? Nope, already has the octet. Nitrogen, yeah, how many lone pairs? 1, it has 3 bonds, so we would give it 1 lone pair. Oxygen up here, how many bonds? 1, how many lone pairs would it need to fill the octet? 3, okay, so we put in 3 lone pairs. This oxygen is in the same situation. How many lone pairs do we have left? 2, so we can only put 2 lone pairs on this oxygen. So we cannot fill its octet. Which leads us to part B. And part B is to form multiple bonds to satisfy any octets that remain to be unsatisfied. Okay, we'll say satisfy remaining octets. Okay, so to do this, what we need is a lone pair on an atom that is bonded to the atom that has the unfilled octet. Do we have that in this case? Okay, we have a nitrogen that has a lone pair on it. And so we can convert that lone pair into a multiple bond, a pi bond, or a double bond in this case, to this oxygen. And now we have fulfilled all the octets of our atoms. Any questions? As I mentioned, once you get proficient at this process, you can kind of combine steps 3A and 3B, but we split them out to go through this particular example. All right, we're not done yet. We have one more step that we need, which is assign formal charges to atoms. Okay. There's a formula. There's a few different formulas for calculating formal charge. The one that I like to use is the group number. That information comes from the periodic table. So you take the group number and you subtract the number of bonds from that group number. And then you subtract the number of unshared electrons. Not the number of lone pairs, the total number of electrons on that atom that are not shared. Okay? All right, so let's go through that process right here with nitromethane. Carbon, what is our group number? 4. How many bonds do we have on that carbon? 4. How many unshared electrons? 0. What's our formal charge? Okay, no formal charge, nothing to write. All right, let's look at nitrogen. Group number. 5. How many bonds? 4. How many unshared electrons? So what's our formal charge? +1. We'll usually just write a plus symbol because the vast majority of the time, the formal charges will be 1, either +1 or -1. If it happens to be a 2, then you would write it in. If not, we just assume that that means 1. Okay, so we have +1 formal charge on that nitrogen. All right, let's look at the oxygen. Group number 6. How many bonds? How many unshared electrons? 6. Formal charge, -1. Okay. The bottom oxygen, 6 minus how many bonds? 2. How many unshared electrons? Okay, 4. So no formal charge here. So as you practice this, what you'll find is that the following patterns, as shown on this table, will emerge. Okay, these will be true. If we have we've seen this example right here. If we have a nitrogen with 4 bonds, that's going to have a formal charge of +1. If we have an oxygen that has the octet and has only one bond, then that's going to have a formal charge of -1. If we have a carbon with 3 bonds and no octet, only 6 electrons, that'll have a positive charge. That's called a carbocation. And then over here, if we have a carbon with 3 bonds and a lone pair, that's going to have a -1 formal charge. That's known as a carbanion. Okay, so you'll recognize these patterns. This is certainly not a table you should waste any time memorizing. This is just a table that once you're proficient at drawing Lewis structures, you'll just look at it and say, yeah, that makes sense. And then you don't have to go through the formula. You just automatically put those charges in. Okay. So there's something I want you to know about formal charges that is important. Formal charges are not real. That's why they're called formal. So in nitromethane, you could calculate the charges. You could use some fancy quantum mechanics-based software to calculate the real charges on the atoms. You would find a charge on that nitrogen, but it's going to be really, really, really small. It's going to be very close to 0. It's going to be plus 0.000 something or other. Okay. And then, as we'll talk about in a minute, the negative charge is actually shared by these 2 oxygens. We'll get to that later. But the point is, formal charges are not real. They are indicative of actual charges, but the magnitudes are not real. You do not have a full-blown +1 charge on this nitrogen in nitromethane. Okay? But they are useful because they do help us understand which atoms in a molecule are electron deficient and which atoms in a molecule are electron rich. Any questions on how we draw Lewis structures? Okay, so let's talk now for a little bit about isomers. Okay, isomers, this is a topic that you've presumably learned about before. Okay, we'll write that over here. Who would like to raise their hand and give us a definition of isomers? What are isomers? Yes, please. Okay, molecules that have the same chemical formula, same molecular formula, but different structures. Okay, so we will call them different molecules. The fact that they have different structures makes them different molecules with same molecular formula. Okay, and so because they're different molecules, they obviously have different properties. Okay, so the atoms have to be arranged differently in order for something to be an isomer. Is there an isomer that we could draw of nitromethane? Let's look at that structure. I'll tell you there is, so maybe I'll rephrase my question. What would an isomer of nitromethane look like? Yes, please? Okay, so we could switch the position of an oxygen or nitrogen. I believe what you mean by that is we could, make that carbon smaller, sorry. We could, instead of having our carbon be bonded to the nitrogen, we could have our carbon be bonded to one of the oxygens instead. Is that what you meant? Okay. And then we could have the nitrogen here, and then we could have this oxygen. Okay. So we need to go forward and draw the Lewis structure and make sure that we can draw a valid Lewis structure to see if this is actually an isomer that would work. So we've got an oxygen with 2 bonds. How many lone pairs should we draw there? 2 lone pairs. Okay. Backing up a minute, how many sigma bonds do we have? We have 6, right? We have the same number of valence electrons, 24, because we have the same molecular formula as nitromethane. So we have 6 sigma bonds and 6 lone pairs to assign. Okay. We've assigned 2 here. We could go on and assign the other lone pairs, but we could also take a little bit of a shortcut at this point and combine these 2 steps if we wanted to. How many bonds does our nitrogen want to form in order to be neutral? It wants 3. And how many bonds does our oxygen want to form? 2. So knowing that, we could say that there's very likely going to be a double bond here between that nitrogen and oxygen. That's a little shortcut combining steps A and B if we have a good understanding of the information in this table. So then how many lone pairs would we put on the nitrogen? We'd put one lone pair here. How many lone pairs would satisfy this oxygen's octet? 2. How many lone pairs do we have left? We only have 2 left because we used one of them to make that double bond. So we have the right number of lone pairs. And if you count it up, you'll find there are indeed 24 valence electrons. And this is a valid resonance structure. Okay. So this molecule is called methyl nitrite. It is not the same as nitromethane. It has the same molecular formula, but because the atoms are connected together in a different way, it is an isomer. It is a specific type of isomer known as a constitutional isomer. A constitutional isomer has, or constitutional isomers, we'll define it in the plural, constitutional isomers have the same molecular formula, but different connectivity of atoms. Okay, so raise that up a little bit. We can see methyl nitrite, nitromethane, same molecular formula, different connectivity of the atoms. Here the carbon is connected to an oxygen. Here the carbon is connected to a nitrogen. Okay. You might wonder, what other possible kinds of isomers could we have? If the atoms are connected together in the same way, wouldn't the molecules all be the same? The answer is, when we start looking at three-dimensional structures of compounds, we will find that it is possible to have atoms connected together in the same way, but have those atoms have different orientations in space. Those are known as stereoisomers. So we haven't gotten to that yet. We'll talk about those starting in chapter 4. So for now, constitutional isomers are the only types of isomers we've learned about, and nitromethane and methyl nitrite are constitutional isomers. Any questions about isomers? Yes, please. You could. So if you were writing the molecular formula out, there's no law that says how you have to write the atoms and what order you have to write the atoms in. So if you were wanting to give someone a clue that it was connected together in this way, you could certainly write CH3ONO. That would be fine. When we draw the Lewis structures, that's when we are saying this is how those atoms are connected together. You could also write CH3O2N, and that would be the same molecular formula. Any other questions there? Okay, so let's talk briefly about, we talked about the octet rule. The octet rule is important for understanding how to draw our Lewis structures. So let's talk briefly about exceptions to the octet rule. Sorry, there we go. Got to figure out which thing to raise. So what exceptions do we have to the octet rule? We just talked about one in the second row. What atom oftentimes does not have its octet? Boron, okay. So we'll just put the exceptions over here. So boron, it can have 8 electrons. I mentioned that it would be negatively charged, but many times we will have molecules with neutral borons that only have 6 electrons. Okay, and those make stable molecules, but they do exist, but they are fairly reactive because they don't have the octet. Okay, another exception to the octet is going to be third row elements, mostly phosphorus and sulfur. Those are the 2 third row elements we will spend the most time looking at in this class. They can exceed the octet. Why can phosphorus and sulfur exceed the octet? Yes, please. Yes, being in a third row, phosphorus and sulfur have d orbitals, and so they're able to put electrons in those d orbitals so they can exceed the octet. So sometimes we will find 10 electrons or 12 electrons around a phosphorus or a sulfur. That's nothing to panic about. If you see 10 or 12 electrons around a second row atom, that should just, you should cringe when you see that. It just shouldn't make any sense to you whatsoever. That goes totally against anything in chemistry. But in the third row, no problem. You can be comfortable seeing 10 or 12 electrons around a phosphorus or a sulfur. And then there's another group of elements that break the octet rule, and that is the transition metals. We're not going to do much with the transition metals until the very end of 352M, but we will talk about the transition metals at that point. The transition metals are the metals right here below the sign. We've got kind of a notch in our periodic table, and the metals that are below that notch are the transition metals, the transition between our metals and our nonmetals. Okay? Transition metals, instead of following the octet rule, they follow the 18 electron rule. Why do transition metals follow the 18 electron rule? Anyone want to raise their hand and take a stab at it? Yes, please. Yes, so how many d orbitals are there? 5. So it can take 10 electrons to fill the d orbitals. So the transition metals are especially happy when they have all of those d orbitals filled. Hence, they follow the 18 electron rule as opposed to the octet rule. Again, that's something we'll address in 352M, so you can file that information away for now. Okay? But it is important to know the few exceptions we have to the octet so that we can draw our Lewis structures properly. Okay, so for the remainder of the time, and then going into Friday's lecture, we're going to talk about resonance structures. And I've told you previously that resonance structures is vital, a vital topic in this class. To be able to understand organic reactions and how they proceed, it is very important for us to understand resonance structures. Okay? To introduce the topic of resonance structures, we're actually going to use an inorganic molecule as an example. We're going to use ozone. Okay. Ozone is O3. It's a vital component of our atmosphere. It shields us from the harmful effect of ultraviolet rays from the sun. Ozone is O3. The oxygens are connected together in a chain like this. And I'm not going to go through it step by step. I'm just going to go ahead and draw a Lewis structure for ozone. And I'm going to go ahead and draw in the formal charges. Okay. All right, so this is a valid Lewis structure for ozone. In this structure, would we have two different oxygen bond lengths, or would we expect them to be the same? Would the bond between these two oxygens be shorter, longer, or the same as the bond between these two oxygens? Okay, I'm hearing some different answers. Someone who says this one's going to be shorter, raise your hand and tell us why it's going to be shorter. Yes, go ahead. Okay, we're not getting there yet. We're just looking at this Lewis structure. Okay. So many of you who've read about resonance structures read ahead and you get that actually the bonds in ozone are the same. But if you look at this Lewis structure, you would conclude that if this were the structure of ozone, this bond would be shorter than that bond. So you would have two different oxygen-oxygen bond lengths. Okay? A short one and a long one. But we can measure bond lengths experimentally. We have techniques known as spectroscopy, a whole bunch of techniques known as spectroscopy. And we can use some of those techniques to actually measure these bond lengths. And when we do that with ozone, what we find is that the oxygen-oxygen bond lengths in ozone are identical. We do not have two different bond lengths. Okay? So that tells us that this Lewis structure does not represent the actual structure of ozone. So how do we explain this? Who would like to raise their hand and explain how ozone can have this Lewis structure but have identical oxygen-oxygen bond lengths? Yes, please.
Well, it's ambiguous where you could draw the right oxygen also be the same chemical structure. So what's actually happening is the bond is it's spread throughout the whole molecule. It's not localized.
Okay. You gave a fantastic explanation of what will take probably the next 5 minutes to go through, but I'll focus on the first part of what you said, which is that there's a second Lewis structure we can draw where you would have a single bond between these two oxygens and a double bond between these two oxygens. So I'll go ahead and draw that Lewis structure right here. Okay. And I'll draw in the lone pairs. This is a mark on the chalkboard. That's not an electron. We don't have 3 electrons around that oxygen. Unfortunately, it's in a bad spot on the board. Okay. So we have a second Lewis structure, equally valid to the first Lewis structure that we drew, where we have a single bond between the central oxygen and the one on the left, and a double bond between the central oxygen and the one on the right. And so these are known as resonance structures. So resonance structures, we will define those as Lewis structures with the same connectivity of atoms, meaning the atoms are connected together in the same way. It's still 3 oxygens in a chain, meaning we have not changed the position of any of the sigma bonds connecting the oxygens when we draw those 2 Lewis structures. Whenever we can draw 2 Lewis structures for a molecule where the sigma bonds don't change positions, where it's only lone pairs and pi bonds that are changing positions, those are known as resonance structures. Okay? Now, we like to use arrows when we're showing the relationship between resonance structures. Okay? So if we were to show the relationship between these 2 resonance structures, we would say if we were going to convert the resonance structure on the left to the one on the right, we would have to convert one of these lone pairs from the oxygen on the right into a double bond or a pi bond. But we couldn't just stop there because that would cause our central oxygen to exceed the octet. So we would have to convert the electrons in that pi bond or double bond into a lone pair on this oxygen. Okay? So we use curved arrows to show the movement of electrons. It's very important. We have arrows are part of the language of organic chemistry. We have many different types of arrows that we draw, and curved arrows with a regular head on them show the movement of a pair of electrons. And then to show that the 2 structures in question are resonance structures, we draw a single double-headed arrow in between them. Please note that this is not an equilibrium arrow. These 2 structures are not in equilibrium with each other. We'll elaborate on that in a moment. They are resonance structures. This double-headed arrow is distinguished from equilibrium arrows. Equilibrium arrows would either look like this, 2 arrows. Sometimes they're 2 half-headed arrows like this. These are not that. Okay? So whenever we have a double-headed arrow, that means that the 2 structures in question are resonance structures, meaning they are 2 different Lewis structures that represent the same compound. So if they both represent the same compound, then the true structure of that compound cannot be represented by any single Lewis structure. It has to be represented by a hybrid of the Lewis structures. Okay? So as we look at ozone, what do we think our hybrid would look like? I'll go ahead and draw it over here. It's still going to have this framework. What kind of a bond are we going to have between these two oxygens? Okay? It's not going to be a single bond. It's not going to be a double bond. It has to be something in between. It has to be a 1.5 bond. We can have 1.5 bonds. Bond orders, there's no physical law that says all bonds have to be single, double, triple, and so forth. We can have bonds that are in between. That's not a problem. Okay? So we have a 1.5 order bond between those two oxygens. What kind of bond between these two? Same thing. We know from spectroscopy that those bond lengths are identical. And if we look at our hybrid, or if we look at our two Lewis structures, double bond here, single bond here, it makes sense that we would need a 1.5 bond there. Okay. Let's look at the formal charges in our hybrid structure. What formal charge would we want on the central oxygen in our hybrid? +1. We have a +1 formal charge on that oxygen in both resonance structures, so we would have a +1 charge in the hybrid. What about the oxygens on the end? What formal charges would we have there? -1/2, exactly. Okay. Formal charges don't have to come in units, and remember, formal charges aren't real. There are actual charges on the oxygens in ozone, and the charge on that central oxygen is twice the charge, the magnitude of the charge on the outer ones. But remember, these are just formal charges. Okay. Any questions on how we came up with this hybrid structure from the two resonance structures of ozone? Okay, yes, please. Excellent question. Is there a reason why I didn't draw the lone pairs? Yes, there is a reason why I didn't draw the lone pairs. The reason is that when you're dealing with partial bonds, now it becomes essentially impossible to draw lone pairs because you don't really know how many electrons to draw. And that's fine. Remember, when you draw Lewis structures, you're pretending that the electrons are anchored in a certain spot. You're localizing them to individual atoms if they're lone pairs, or to bonds if they are, in between two atoms if they're in a bond. Okay? But the reality is that electrons can be delocalized. Electrons are able to move throughout a molecule. And when we have the ability to draw resonance structures, that comes from the fact that we're able to move, those electrons are able to move. An individual Lewis structure does not show any movement or delocalization of electrons. And so when we have the ability to delocalize electrons in a molecule, one way to show that is by drawing resonance structures. Another way to show that is to draw a hybrid, and the hybrid is more representative of the actual structure, which is nice, but the problem with hybrids is what you identified with your question, that you can't draw in the lone pairs. Okay? And when we are going to be drawing reactions and reaction mechanisms, it's a lot easier for us to understand reaction mechanisms by thinking about lone pairs and where they are and so forth. So even though resonance structures aren't real representations, we're still going to use them quite frequently when we are drawing compounds. We'll use them more frequently than we'll use the hybrids, in fact, because even though they don't show the complete picture of the structure, they do make it easier for us to understand properties. Okay? So it's important for us to be able to draw resonance structures and hybrids, but we're going to deal with resonance structures primarily in class when we have the ability to draw them. Okay? Can we draw a resonance structure of nitromethane? Okay, who can raise their hand and tell us how we would do that? Yes, please. Okay, so we would have a double bond here instead. If we're using our curved arrows, we would convert one of these lone pairs to a double bond, and then we would move electrons in this double bond to make a lone pair on that bottom oxygen. Okay, and I'm not going to draw the hybrid for you based on what we went through with ozone, you should be able to draw that hybrid structure on your own. Okay? There are some key principles related to resonance structures that are important to remember. The first one we've gone over, the real structure is a hybrid. When you can draw resonance structures, one individual resonance structure does not represent the structure of the molecule. Ozone does not have different bond lengths. It has one bond length, and so the real structure is the hybrid. Okay? That's an important thing to remember. The second point to remember is that resonance structures are not in equilibrium. They are not interconverting. If resonance structures represented two compounds that were interconverting, then with ozone, we would have two different bond lengths. And those bond lengths would be oscillating or switching back and forth. Right? This oxygen-oxygen bond length would be constantly lengthening and contracting, and the other one would change in a corresponding fashion. That is not what's happening. The bond lengths are the same. So we do not have an equilibrium between our resonance structures. Another way to state that, I'm going to put it as a third point because it's so important to remember, is that resonance structures are not isomers. They are two different Lewis structures representing the same compound. Okay? Questions about these principles of resonance? Okay, so let's go over some rules relating to resonance structures. We'll call them the rules of resonance. Okay, there's about 6 of them that we'll go through that will help us in drawing resonance structures and also help us when we compare resonance structures. In the examples we've drawn for you so far, these two resonance structures are equivalent to each other. They're not identical, but they're equivalent. Okay? And when they're equivalent, the hybrid is exactly in between, as we have over here with ozone. But that's not always going to be the case. So these rules are going to help us to compare resonance structures in cases where they're not equivalent in many cases. Do you have a question? Okay, no problem. All righty. So let's go over these rules of resonance. The first rule that we're going to have is that for structures to be resonance structures, the connectivity, which is the single bonds connecting those atoms, must be the same. Sorry. So only positions of multiple bonds and lone pairs can change. Okay? So if you look at two structures and the sigma bonds are in different positions in those two structures, those structures are isomers as opposed to resonance structures. And all the resonance structures we'll look at, it's only lone pairs and multiple bonds that are going to differ. Okay? Any questions about that? So the connectivity is the same, making them the same compound. Okay? Second rule that we have, octet must not be exceeded by second row elements. Okay? If you're trying to draw a resonance structure of a compound, and you end up with a structure where you have exceeded the octet on a second row element, that is invalid. Okay? That is not going to be a valid structure. Okay? All right. Our third point, our third rule is going to be, this is going to apply when we are comparing two resonance structures to each other and trying to determine which one is more stable or lower in energy. In these cases, the more stable structure has the least amount of separation between oppositely charged atoms. Okay? So that should say more stable structure. Sorry, I forgot to write stable in there. So the more stable structure would have the least amount of separation between oppositely charged atoms. We'll show you an example of what we mean by this before we let you go. To do so, I'll draw the isomer of nitromethane that we showed you before, methyl nitrite. And as I'm drawing this, I want you to think of how we could draw a resonance structure of methyl nitrite. Okay? Who can raise their hand and tell us how we would draw a resonance structure of this compound? Okay, please. So you're saying we could have a double bond between this oxygen and the nitrogen as opposed to this oxygen and the nitrogen. Is that right? Okay. So to do that with our curved arrows, we would have a curved arrow originate from one of the lone pairs on the oxygen to make an oxygen-nitrogen double bond here. To avoid exceeding the octet for the nitrogen, we have to move electrons in a pi bond and make them a lone pair on that oxygen. Okay? So that will give us a structure looking like this. Okay? And we have formal charges here according to the patterns from this table, formal charges on these oxygens. Okay? Which of these resonance structures will be more stable or lower in energy? The one on the left or the one on the right? The one on the left, exactly. We have no charged atoms, no formal charges. So by default, we have the least amount of separation between oppositely charged atoms. Here, we have one atom in between our oppositely charged atoms. Okay? So this is an example of this rule. What this means is that the hybrid structure for this molecule would look much more like the structure on the left than the structure on the right, meaning we would have charges, but they would be very close to zero. Charge on this oxygen, very low positive number. Charge on this oxygen, very low negative number. Okay? Bond between these two atoms, very close to a double bond. Bond between these atoms, very close to a single bond. Okay, any questions? All right, that's all we have for today. If you have an information sheet to turn in, just leave it on your way out. If you did not pick one up, you can come up and grab one from us, okay?